Hello, Assalamualaikum, selamat pagi, good morning. Welcome back to SIG 2004. This is Sedimentology, Part 1, Siliciclastics. This is lecture number 2. In the previous lecture, we looked at the textural properties of sedimentary rock, such as grain size, grain morphology, grain fabric, and also the concept of textural maturity. Today, this is lecture number 2. We will be looking at two more properties of sediments and sedimentary rocks, which are porosity and permeability. These two properties are secondary and derived from the textural properties. So before we go into definitions of these two properties, let's have a look at what sedimentary rocks are actually made up of at the microscopic scale. So I have a cartoon here, a zoom in of a sandstone sample, and this is what you get under the microscope. First, you have the solid grains, which are which are your grains, right? Be quartz or feldspar or anything, right? So these are called your framework grains. Okay, they form the skeleton of your sandstone. Sometimes you have finer grain particles between the framework grains, and this is called the matrix. Okay, so you have sand grains and maybe you have silt grains in between. Then you might have empty space between your grains. Okay, and these empty spaces are called pores. Okay, those are the space between the grains. Your pores can be empty. Doesn't mean it's a vacuum, but it can be filled with gas, or it could be filled with a liquid such as water or oil. All right. Now, the contents of the pores can be economically important. Like I said, right, water or oil, right? Now, so we need to have a method to determine the, the percentage or total volume of pores that are in a sedimentary rock reservoir. Okay, so we go to the next term here, porosity. Porosity is the percentage of void space. Void space means the pores inside the rock. Okay, so the equation is here. Porosity equals the volume of void space, because how many holes you have, in terms of volume, right? Divided by the total volume of the rock, meaning the volume of your grains plus the pores. Okay, and after this you get the percentage, and that is your porosity. Okay, so you can say that maybe your sandstone has a porosity of 30%, and that is good porosity. Yeah, there are a lot of holes inside your rock, or 15%, which is a lower porosity. Okay, so that is how you measure the volume of holes inside your rock using the porosity. Yeah. So porosity in sedimentary rock comes in many forms, but you can actually classify them into two main types. First, you have what is called primary porosity, and then you have secondary porosity. So we go through this one by one. Let's look at primary porosity first. Okay. So these are pore spaces between primary grains. What do you mean by primary grains? These are grains which were just deposited, and have not undergone any alteration through burial or diagenesis. Okay, so you can imagine a river transporting sand to the sea, and all this sand is laid down on the seafloor, right? So it has not undergone any burial under more and more sediment. There is no diagenetic alteration of the sediment. So any original holes inside the sediment is called primary porosity. Okay. So the most common type of primary porosity you see is what we call intergranular porosity. These are pores which occur between your framework grains. All right, so that's intergranular porosity. So I have zoom in under microscope here. I have a sandstone sample. So you can see the quartz grains, right? Here. And notice the shadowy parts. These are the holes, right? These are your pores. And the pores occur in between the grains. So this is intergranular. This is primary intergranular porosity. You can also make a, let's say, a thin section of the sandstone sample. And then you inject an epoxy resin into the sandstone, and the epoxy resin will fill up the holes in between the grains. Okay, so this is what you get after you polish a thin section. So the white colored material here are quartz grains. Right? These are your framework grains, and the pores have been filled in with blue epoxy in this case. Okay, so yeah, in this case, you have relatively good porosity, lots of holes in between the grains. So this is primary intergranular porosity. Another type of primary porosity you can get in sediment and sedimentary rocks is what we call intragranular porosity. But this is more common in carbonate or mixed silicic and carbonate sedimentary rocks. Sometimes you have, let's say in this case you have shells. These are fossil shells of snails or gastropods, right? And you know that fossil snails, the shells have holes inside them, right? And holes are porosity. So in this case, the holes are inside the grains. We consider the shells as grains. They're not really in between the grains, but inside the grains. So this is primary intragranular porosity. Space is inside the shells. Okay, so that is primary porosity. It just is the original porosity that you have directly after deposition. But we know things happen after when we bury sediments under more and more sediment load, right? You've learned about lithification and diagenesis during first year, right? And these processes can affect porosity. You can actually form new porosity because of burial and diagenesis, and also tectonic deformation. Okay, so all of this happens after deposition. So we call it secondary porosity. For example, you can have pore space which is formed by dissolution or fracturing. Let's look at the photo here on top right here. This is a sandstone sample under thin section, okay, under microscope, sorry. Okay. So you can actually see some component, a few things inside the photo here. First, you have the white colored minerals, which form sand grains, and this is quartz. Okay, I'm labeling it Q. So these are quartz grains. Then you have the slightly dirtier grains here. You have a dusty appearance to it, right? And these are feldspar grains of sand. Okay, so you have feldspar and quartz grains in your sandstone here. Right? So you also have these lithic fragments also, okay, MS. So these are mudstone samples. Mudstone grains. And then you have the blue colored epoxy filling in the pores. So the blue parts here represent porosity, okay, fire. Okay, so this is porosity. Now I want you to focus on this part. It's labeled F, right? So this was originally a grain. You can still see the remnants of the mineral here, the white colored parts here. It was a feldspar sand grain, but it has been dissolved. And we've learned that between quartz and feldspar, feldspar is more unstable and it can weather out into clay. Okay, so because of the dissolution of feldspar, you get new porosity here. So this new porosity inside the grain here, this is secondary porosity because of dissolution. So you have primary porosity, interparticle or intergranular, right? And then you also have secondary porosity due to dissolution. You can also get porosity formed due to fracturing. Let's say you have a mudstone which has been buried under an overburden of maybe several kilometers thick of sedimentary rock, right? And let's say it has undergone tectonic deformation and faulting. So this part here has been intensely fractured, right? Now remember, fractures are also holes, space which can be filled in with fluids, right? So this is also porosity. Doesn't look like this, again, not that like these nice holes, but yeah, in this case it's more polygonal. But yeah, this is also porosity, but secondary fracture porosity. Okay, so that is porosity. It is a measure of the volume of open pores of pores you have in the rock, right? Divided by the total volume of rock. So you get a percentage. Right? The second property now we are looking at is permeability. So what is permeability? It is defined as a measure of the ability of a porous rock to allow fluids to pass through it. It measures the resistance with which a rock opposes movement of fluid through its pores. So look at the cartoon here. This is a sand, and you have sand grains here, but you also have pores, right? Now pores are good. They can store fluids, right? Water and oil and so on. But it's not. We don't just need to know about pores. We need to know how the pores are connected to each other. They need to form a pathway. They need to be able to, if you have any fluid, it needs to be able to flow from one point, let's say from the bottom here, to other point, like a channel, right? Or like plumbing, basically, right? So the ease in which the fluid flows from one point to another point is permeability. Okay, so a single isolated pore has no permeability, but lots of pores which are connected to each other has good permeability. So how permeability is calculated or determined? Yeah? I'll give you an example of how you do it in petroleum geology. How do you determine permeability of of rocks containing hydrocarbons? Right? How easy will the hydrocarbons flow inside your rocks? First, you take a sample of the sedimentary rock, which is cylindrical in shape, bentuk silinder macam ini. Then you try to flow a liquid from one end to the other end. Okay. Then you use Darcy's equation to calculate permeability. Okay. So given a liquid is allowed to flow through a cylindrical rock sample under pressure, the following relationship occurs. Okay. So what you have here is K, which is permeability, which is what you want. Then you have pressure difference between the incoming flow and the outflow, P1 minus P2. Okay? This pressure on this side, lari dia keluar. Then you have the cylinder length, the flow rate of the fluid, cubic centimeters per second, the cross-section area, and also the viscosity of the fluid. Okay, so you can arrange this equation to get permeability. Okay, so that is Darcy's equation. So the SI unit for permeability using Darcy's equation is meter squared. But in practice, I'll give you an example in petroleum. In petroleum reservoirs, we use another kind of unit, which is a practical unit called the Darcy or millidarcy. Okay, so 1 Darcy is equivalent to 0.9869233 micrometer squared. Okay, almost 1 micrometer squared. Okay. So in petroleum geology, we say that if you have a permeability in the range of tens of millidarcies, it's a poor reservoir, right? With low permeability. If you have permeability at the scale of hundreds of millidarcies, that is fair to good, an okay reservoir. But yeah, if your permeability of your sandstones, let's say, is up to one darcy or even more, 1 darcy is equals to 1000 millidarcies, that is a very good reservoir with very high permeability. Alright? So that's how you calculate that's permeability. So I'll stop here first. We'll go to we'll look at the relationship between porosity, permeability, texture, and also diagenesis in the next part of this lecture.